So just starting the recording now. So the lesson today is on conditional probability. So again, this is just going, if you're looking at the textbook, it's going to be section 4.4 there, okay? So what we're going to talk about today is just about what conditional probability means and how we can use that to solve problems. And then we're going to talk about the multiplication law for conditional probability. So we'll talk about that in a little bit. We're going to kind of connect the idea of conditional probability with the intersection of sets. Okay, so we're going to kind of link up the two concepts. And again, you don't have to write this part down. This is just mainly for me to kind of explain to you. So first thing I want to show you guys is the Monty problem. Has anyone heard of this? Nope? Okay. So I just want to play this little problem to you. It's kind of interesting.
I hate math, but there's this statistics problem that has me geeking out. It's a question that seems really, really simple, but it stumped me. And not just me, it has stumped thousands of people around the world, including math professors and leading statisticians. But before we dive in, I'm going to introduce you to Zachary Crockett. He first introduced me to the puzzle, and I called him up to talk about it.
My name is Zachary Crockett. I'm a writer for Priceonomics.
Zachary and his girlfriend were stumped by the problem too.
We just sat there debating the answer to this problem for 2 hours, and I don't think either of us really understood it.
The puzzle we were all stumped by is called the Monty Hall problem, named after the host of the game show that made it famous, door number 3. Now, here's the question. You're allowed to change your answer to door 2. Do you switch, or do you stick with your original choice?
But yeah, I got interested in the Monty Hall problem, did a little research, and then I found out there was this whole kind of second angle to the story.
Never met a man who feared you a little bit because he thought you were much brighter than he was.
That's Marilyn Bossavant in 1988 being interviewed by Joe Franklin.
Well, yeah, maybe I met a man like there too. Maybe a couple hundred like that.
Marilyn is very intelligent. In fact,
back when the Guinness World Records actually kept track of this, she was the world's highest IQ.
She now writes for Parade magazine and has for the last 20 years.
So the premise of the column was, of course, here's the person with the world's highest IQ here to answer your challenging math questions.
This brings us to September 9th, 1990, when a reader submitted to Marilyn the Monty Hall problem. Is it to your advantage to switch your choice of doors? Now, if you're like me, the obvious answer is no. There are 2 doors, so the chance of getting a car and not a goat is 50-50. Bing, bang, boom. But that's the wrong answer. And Marilyn knew that. She replied, yes, you should switch. And here's why. Here are 3 doors. There's a goat behind 2 and a car behind 1. In a blind test, you're more likely to pick a goat than a car. In fact, you're 2/3 likely. So let's use that as the main scenario. You pick door 1. So now Monty Hall, who knows what's behind all the doors, is forced to reveal a goat, regardless of the door you pick. Since in the most probable scenario you've also picked a goat, the only door left is the one with the car. So now Monty Hall asks, would you rather keep the door you've picked, or would you switch? Well, you should most definitely switch. If you do, you get the car 2/3 of the time. Turns out, when Marilyn correctly answered the Monty Hall problem, she received thousands of letters from across the world, telling her she was flat out wrong.
I think part of her was kind of a little bit surprised that she received 10,000 letters calling her an idiot.
There was, without a doubt, a little bit of sexism at play here. Not only was her answer right, it wasn't anything new.
The first time that the Monty Hall problem was really conceived was in 1975. So this guy named Steve Selvin at Berkeley presented this problem in the American Statistician. He contested that the odds are 2 out of 3, and no one argued with him. You know, over the next 15 years, multiple other academics reiterated the same problem, and no one ever told them they were wrong.
Then, in 1990, Marilyn answered the same question correctly, and people went bananas. Marilyn ended up tallying up what percentage of the 10,000 responses claimed she was wrong. Only 8% of readers actually agreed with her, and after subsequent columns, she was able to raise that to only 56%. And among academics,
it was 35% among academics initially supporting it. Around 70% of academics ultimately decided to agree with her.
The only way she managed to get people on her side was by asking them to do the experiment themselves. Elementary, middle school, and high school teachers from all over the country wrote in, astounded that their students were able to prove her right. It's easy now to do a simple Google search of this little sucker of a problem and get a million explanations on how to arrive at the right answer.
There's something about this problem that really strikes a chord with not only statisticians, but just everyday problem solvers and people.
So this right here is actually an example. And again, I don't know if hopefully you kind of follow the problem. It is a little bit difficult, and it's one of those examples in math where it seems it seems obvious. Like in your head, you're probably thinking it doesn't make a difference, right? Like it's 50-50 that you have. If they eliminate one of the choices, it's 50-50 chance that you get the prize. So you would your instinct is to stay with your initial choice, but it's actually in your best position or your best chance to actually switch doors. And it's one of those things that intuitively it doesn't really make sense, but when you look at the actual probability of what's already been chosen, it does make perfect sense, right? So what is conditional probability? So this kind of ties in with this, and you definitely don't have to write the first line on there. This is just kind of explaining to you why this is related to it. So conditional probability is the probability that an event given the it's a probability that an event, given that another circumstance has already happened, it's the probability that an event happens given that something else already occurred, right? That's essentially what we're looking at. So, for example, that last example, what's the probability that you pick the door, that the prize is behind this door, given that the host showed you the other door, right? So it's a probability that depends on another event happening right before it. So the reason it's called conditional probability, obviously, is because of the extra condition that there is an event that happened right before the one that you are currently interested in. So what really happens in conditional probability is we decrease our sample space, and because we decrease our sample space, it becomes most of the time, the event becomes much more likely because you have actually decreased your choices, right? You already know that, so for example, you might already know that you picked, let's say you're rolling 2 dice, and then you know that, for example, the sum is greater than 10. If you know that the sum is greater than 10, then you're kind of more limited in terms of how many results you could possibly have, right? So your sample space goes from 36 to something much smaller, right? So that's an example of a conditional probability. We'll definitely look at some examples to make it clear. So if we want to find the conditional probability, we have a couple special notation that we use. The notation we use for this is a little symbol that looks like this. So it's probability of event B / A. So what that means is the probability of B occurring, given that A has already occurred. And how do we actually find the probability? What we do is we find the intersection of A and B. So we find out what's the probability of A and B happening, and we divide by the probability of A. And hopefully this kind of makes a little bit of intuitive sense. I know we don't talk about the proofs as much, but I hope that even if you, I hope you're not just memorizing the formulas. Hopefully it kind of makes sense, right? What we're essentially saying is A already happened, event A already occurred in this scenario. So because event A already occurred, we are going to be dividing, that's kind of, it's almost, think of it this way, it's almost like that's our new sample space, right? That's what we're really interested in. And what we're really doing now is trying to figure out, okay, now that I know that A already occurred, I want to just focus on the probability of A happening alongside B. So the two of them have to happen simultaneously. Is that going to make sense? So that's what we're doing in the formula, is we're taking the probability of A and B, which is the intersection, and we're simply dividing by the probability of A, which is the event that already occurred. So for example, you might be tossing, going back to the coin example, I might be tossing the coin and I might try to give you like a bit of a riddle when I do this, and I say there's at least one heads in the toss, in the 3 coins. So if I tell you that there's at least one heads there, what can I eliminate from this from all these options? Yeah. Yeah, exactly, right? So the one, all three tails is automatically eliminated. So now my sample space becomes a little smaller. And then I might have a question now for you. I might say, what's the probability that I get 3 heads? And this is really simple. The probability to get 3 heads given that there's at least 1 heads, right? So in this case, it's going to be 1 out of the possible 7. So it already got reduced from what it used to be. So that's a good example of how our sample space reduces with conditional probability. So there are different ways of doing this. We can either solve conditional probability using a formula, or we can solve it by reasoning out the new sample space and comparing it to the event space that we're interested in. So let's just look at an example here. So let's say that you're drawing a card from standard deck. And whenever I talk about the standard deck, we always assume it's 52 cards, unless I tell you otherwise. There are some questions in the textbook that include the joker. I tend to not include the joker. I just feel like that throws things off a bit more. I always just do 52, okay? So what's the probability that that a randomly drawn card from a standard deck is a face card? So let's just start with that one first. So what's the probability that I pick a card and it's a face card? 12 out of 52, exactly. So there's 12 face cards, exactly. So I'm actually going to write this down. The number of face cards is 12. And so, and I don't know why I wrote it small. So there's 12 of them, and then obviously 12 out of 52, which you normally want to reduce, right? So that gets reduced to, and I'm showing all the work here, gets reduced to 3 out of 13. You don't have to show every little step here. I did it for you guys just to make sure you're kind of following along. So essentially all we're doing is finding the probability of choosing a face. So right now we're not doing any conditional probabilities. It's just normal theoretical probability, right? Small thing to note, there's a reason I wrote B. If you're wondering why I didn't write A, it's just because I'm kind of linking it up. The second part of it is then asking you what's the probability that you randomly draw a card and it's a face card. So pretty much the exact same question, but now we have an extra condition here. So it's given that the card is a spade. So now we're told something extra on top of it. So what's the probability that it's a face card if I know that it's a spade? So I know it's a spade, so that automatically reduces my options a little bit, right? So now this is basically my event B. This is the one that I'm interested in. And event A is the one that already happened. So I'm going to put right here, already happened. So according to the formula, what I'm going to need to do, and I'm going to show you 2 ways of doing this. I'm going to show you how to do it with the formula. And I find with the formula, sometimes it ends up being really long. Then I'll show you without the formula, and I feel like sometimes it's just easier to not use the formula. I'm going to show you both of those. So what we're going to do is find the probability of getting an getting a spade, and then I'm also going to find the probability of getting a spade and a face card. Okay, so we're going to kind of do both. Going to go to the next part, guys. All right. So again, just explaining what I already said. So what we're going to do is we're going to find the probability of getting a face card if I already know I got a spade. So what I'm going to do is I'm going to find the probability of getting a spade, and this should be pretty easy. What's the probability of getting a spade? Yep. Yeah, 1/4 is exactly 13 out of 52, which is 1/4. I definitely recommend reducing it for your own sake. Actually, it'll make the math a lot easier. If you reduce it, it becomes much simpler. One thing I've noticed in the back of the book, they don't actually always reduce the answers. I don't know why they don't. They really should, because it probably makes it easier. But again, on the quiz, I'm going to be a little more picky. Make sure that you actually reduce it, because I can't have multiple right answers. I can only have one. But on the test, I'm a little more flexible with it. But as a general rule, try to reduce it. So we know that there's only 3 cards out of the 52. So what we're going to do next is look at the cards that are face cards and spades. So how many cards are face cards and also spades? Well, there's Jack, Queen, and King that are all spades. Does that kind of make sense? So we have the Jack that is a spade, and the queen. I was gonna try to draw the. Oh geez, I'm just the worst at drawing. Okay, so yeah. Oh my gosh. See, the first one worked out, but the other ones did not. Okay, so I basically have the 3 cards that have the 2 conditions I want. They're face cards and they're spades. So the probability that I have a face card and a spade is 3 out of 52, right? So there's 3 of them out of the total 52. Actually, I kind of skipped this up there. I just wrote down the number, 3 out of 52, which I don't think that reduces at all, so we just leave it as it is. So now we just put it all together. So what we're going to do is use the formula. The formula says take the probability of the intersection divided by the probability of the event that already occurred. So I'm going to take the intersection, which is 3 out of 52, divided by 1/4. So what does that give me? 3 out of 52 divided by 1/4. So doing a little bit of math here, what happens when I divide fraction by another fraction? Yeah, flip it and multiply. You guys remember that rule? Yeah, flip it and multiply. So you have to flip the second fraction and then multiply. So if you forgot division with fractions, I feel like it's probably not a bad idea to review that. I feel like people sometimes forget. Don't forget you have to flip the second fraction and then multiply. So when you do that, you end up getting 3 out of 52 multiplied by 4 and 1. And again, if you're really good at simplifying, you're really good at, how many of you remember those little techniques in advanced functions, how to cross cancel or functions? You can do this. You know that 4 goes into 52 13 times. So this reduces to 1. And then you can do 3 times 1, which is 3, 13 times 1, which is 13. So 3 out of 13. If you're looking at that and you're like, what the heck did you just do? Don't worry about it. You can always do 3 times 4, which is 12, divided by 52, and then you can still reduce it. You'll still get the same answer. I always try to find little tricks to make it easier for me. Everyone okay with that? Okay. So, did anyone find that a little bit confusing for this type of question? Yeah, because the question is actually, it seems like it's complicated, but it's actually not. It's essentially saying, what's the probability that I get a face card, which is king, queen, or jack, if I know it's a spade? So there's actually, in my opinion, there's a much easier way to do this without formula. And again, there are times where you don't have to use a formula. But the reason, again, we go over the formula is because it's not always going to be that easy. So in this case, we're told that the spade is these cards. So we're told that automatically we have a spade. So that automatically reduces our sample space. So instead of looking at all 52 cards, I'm only going to look at these 13 cards. And then the question is, what's the probability that it's a face card if it has to be one of these cards in this green box? So there's only 1, 2, 3 face cards out of the possible 13. So the probability of B given A is just 3 out of 13. Is that going to make sense? Or no? Yeah, Jess?
Does it matter which side it is?
No, it doesn't matter. I could have made the original, the one that happened before B and the other one A. You can switch them, but then it changes your formula around a little bit. So had it been, I think this is what you're asking me. Like if it had been probability of A given B, if that's what you're going to go with, so B is the old one, this is the new one, then you have to, everything is the same except you have to divide it by B, the probability of B. That's the only difference. Does that make sense? Yeah, good question. So you always divide by the probability of the event that already happened, right? That's basically what you're limiting. So that's if you're using the formula, make sure you know the 2 variations of it so you don't get confused. But hopefully you don't memorize it, right? Hopefully it just kind of makes sense. You're dividing by the probability of the event that already occurred. Does this make sense? Who found this a little bit easier, this one? Just a visual drawing, yeah. You can do it both ways. It doesn't really matter. On a test, as long as you explain it to me in some way, it's fine. I may sometimes ask you to use a formula, and sometimes you actually don't. Some of the textbook questions, you don't have a choice. They actually don't. They don't actually tell you. They don't draw it out for you. All they do is give you the probabilities. So in that case, you have to use a formula. So sometimes you're kind of forced into it. But in this case, I'm just showing you a different alternative. you can literally draw it out and say, hey, I know it's a spade, so I only have 13 options, right? I don't know why I did this. I only have 13 options, right? I don't have 52 options. And of those 13 options, only 3 of them are the ones that I want, the base ones. Does that make sense? Cool. So next part, reading a table. So I'm going to go over this pretty quickly. This isn't too relevant, to be honest with you, and it's not really linked to everything else. But this is more good for you to know, especially when we get to the statistics unit, how to read a table and understand it. This is extremely critical. So like Mr. Arden was just saying, like knowing how to read data like quickly, right? Getting a good sense of what it means. So we'll just do this one together. So a survey of 1,000 people asked whether they wear glasses while driving. Don't worry about writing this one down. We can just do this one together. And these people were tested to see whether they need eyeglasses while driving. So the results are displayed here. So if a person is selected at random from this group, determine the probability that the driver does not wear eyeglasses while driving, even though they need it. And that's also super dangerous. I don't know why they're doing it. So what's the probability that we pick someone that has that? So this is just good practice with reading a table and kind of interpreting what it means. So, yeah, yes. 14%. So how'd you get that?
Sorry.
Oh,
Would it be 140?
yeah, you got it. There you go. So needs to wear. So we go right here. So 140, right? And we know that this is needs to wear. But they don't actually wear it while they drive. So that's 140 divided by 1,000, right? That's 14%. That's correct. Perfect. So again, it shouldn't be too bad. I just wanted to review how to read tables because there's a couple questions that deal with that. And either way, this is really good for you to know because I don't know if it's just me, but I remember the first time I learned how to read these tables, it is confusing for some reason. It's just the way it looks, it's a little odd the first time. And just make sure you know how to like kind of make the connections between the different variables. And we can do another one. So we have a student. So Matt is surveying students in the class, and he's summarizing from the question, "Do you like school?" So find the probability that a student dislikes school, given that the student is a male. And again, don't worry about copying this table down. It's actually it's in your textbook. It's page, if you want to look at it so you don't have to copy it, it's page 235, number 1. So it's one of the homework questions. I just switched the question around a little bit. Yep.
Is it 5 out of 30?
Sorry?
5 out of 30.
5 out of 33. You have almost the right idea. You're close. Sorry? 5 out of 19, yes. So the first thing, so you are correct on this. There's 5 of them that dislike it, the 5 boys that dislike school, right? But because we're told here, it says that the student that we pick, whoever we surveyed, we found out that they're male, right? So what's the probability that we had already picked a male, and then that male that we picked didn't like school? So it's actually going to be 5 out of the 19. So it's not going to be out of the grand total. It's going to be just out of the total just for the boys because we were told that we picked the male. So that extra little part in the question kind of threw it off a little bit, right? So normally, yes, it would have been correct. It would have been 5 out of 33. But in this case, it's 5 out of 19 because we're just looking at the boy population, right? Does that make sense? Okay, cool. So just want to make sure you kind of understand how to read those tables. Those can, like I said, they sometimes can be a little bit strange, just the way that they're made, right? So let's look at another example, sum of dice. So let's say that we're rolling 2 dice and then we want to find the sum of the 2 results. So again, for this question, I'm actually going to make it a little bit easier for you. I'm going to give you the table. And again, I'm not always going to give you the table, but at least for this unit, I will give you the table just because we haven't talked about the bit of a shortcut that we can use to find all the possibilities. So for most of these questions, I'll give you the table so you can have a good visual of all the outcomes there. So for the first part of the question, it says, what's the probability that we roll 2 dice and we get a sum of 7 or more? So let's just do the first one there. And I should probably explain how to use this table because I feel like I didn't actually explain it in the lesson there, in the video. So what we're doing is we're basically matching up. We're considering all the different combinations by looking at this table. So it's kind of like the multiplication table, right? So we have 1 matching up with 1, that gives the sum of 2. 1 matching up with 2, that gives the sum of 3. 1 matching up with 3, that gives the sum of 4, and so on, right? So altogether, this lists out all the different possibilities when we roll 2 dice. So what's the probability that we roll 2 dice and we get a sum 7 or more? Sorry? 5 and over 6? No, good guess. So we can look here and we're just going to try to count all the outcomes that are 7 or more. So we're looking at the sums. So the actual sums that we're looking at are the ones in red. So how many of them are 7 or more? So we kind of notice a pattern with this. They kind of are, the ones that are on the same diagonal are all the same. So we kind of notice that 7 or more is going to be on this side of the table, right? So how many of those outcomes do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So 21. So I have 21 that are 7, 21 outcomes are 7 or more out of how many? Yep. 21 out of 36. So that means the probability of getting 7 or more is 21 out of 36, which reduces to 7 over 12. Perfect. So the probability of getting sum of 7 or greater is 7 out of 12. Just watch out for these questions. I feel like this one in the quiz also stumped a few of you. Just be careful with that. And again, because I feel like it would have been easier if we had gone over these examples together. But hopefully this table kind of makes sense. Is anyone confused by this? Or yeah.
So with 5, you essentially some of them twice because you can have a 6 for 1 and
You do, yeah. So this is what confuses everyone because they're like, aren't those the same outcome? But they're actually different though, right? Because when we do this, we assume that the 2 dice are actually different. Like, imagine if they're like different colors. So 1 is green and 1 is red. So a 1 here and a 6 there is different than the 6 being on the green and the 1 being on the red, right? They are actually different outcomes. So I know that I get what you're saying, and this is where people get confused because they're like, aren't you repeating? But actually they are different though, right? Because we're saying that, like imagine that like this is the first die, like let's say that we keep track of like the first and the second. This is different, this is a different order, right? So in this case, it doesn't actually make a difference. So the 1 followed by 6 is different than the 6 followed by the 1. Does that kind of make sense? Yeah. It is a little confusing sometimes. I know what you mean. And that's why like people are surprised at how many more outcomes you get, right? Because we have to think of all the combinations there. So we did the first part there. That's the probability that I get just sum that is 7 or more. So the second part is a little different. So adding on to it, says what's the probability that I get a 7 or more, a sum of 7 or more if the first die that I roll is a 5. So what if I'm told that the first one is a 5? We can actually do it 2 different ways. It's totally up to you what you prefer. Someone have a minute? So we can do it 2 different ways. I can actually do it with the formula, or we can do it without the formula. I feel like let's try without the formula. So these are the only options that we have, right? Because we were just told in the question that I already rolled a 5. So that means I'm going to start limiting my options a little bit, right? So if I only rolled a 5, so I'm actually going to erase this. So it says I rolled a 5 in the first one. So if I rolled a 5 in the first one, then I'm only looking at these options right here, and actually specifically the one in red. I'm not including the 5 there at the top, doesn't count. So I'm only looking at those 6 options there. And then it says, of those 6 options, what's the probability I get a sum of 7 or more? Yeah.
Would it be 1 to 6?
I feel like you gave me the compliment. I think you gave me the compliment. 7 or more. So we're only looking at these possibilities, right? Because this is the one that has 5 as the first die. So it would be?
It'll be 5 out of 6.
Yeah, exactly. It's going to be 5 out of 6 because we have 1, 2, 3, 4, 5. And so it's going to be a total of 5 out of 6, right? So the probability that I get B given A would be 5 out of 6. Does that kind of make sense? So then that's one way to do it, like with the table. But you know what? For this one, let's do the actual part. Let's actually go through the steps. Okay, so for part B, it says find the probability that we get a sum 7 or greater given that we got a 5 on the first die. So let's go through step by step here. So what's the probability that I get a 5 in the first die? Yeah, that's 1 out of 6. And I think that's where you're talking. Yeah. Now again, where you're, yeah, so that's where it does come from. So it's 1 out of 6, right? That's the probability I just get an A. So now we just piece everything together. What's the probability that I get a 5 on the first die and a sum that is 7 or more? So there's actually only a couple options here. You have 5 and 2, 5 and 3, 5 and 4, 5 and 5, and 5 and 6, right? So we have 5 different ways that I can get a 5 in the first die, but a total sum that's 7 or more, right? So basically all the combinations with 5 except for 1, right? 5 and 1 doesn't work because that's still less. But 5 and 2, 5 and 3, 5 and 4, 5 and 5, 5 and 6 all work. So that's a total of 1, 2, 3, 4, 5. That's 5 options, 5 outcomes. So the 5 outcomes is then divided by 36. Find the probability of A and B. Is everyone following so far? I feel like you might be getting a little lost. Are you okay? Is anyone confused? Just ask. No? Okay. You can be honest and just say you're not sure. So we're just going step by step here. So in this first one, we are finding the probability of the event that already occurred. So the event that already occurred is that we got a 5. It's 1 out of 6, right? It's pretty simple. Then for the next one, we're looking at the probability that we got a 5. So I'm going to draw out the picture that we got a 5 in the first dice. But on top of this, we need to make sure that we have a sum that is 7 or more, right? Either 7 or more. We don't know which one, right? So we have to just think of how many outcomes are possible, right? So we have 5 and 2, 5 and 3, 5 and 4, 5 and 5, 5 and 6, right? So basically all the combinations except for the 1. So that's a total of 5 out of 36. So what we're going to do now is just put it all together in the formula. The formula says take the probability of the intersection, divide by the probability of the event that already occurred, and divide them up. So you have 5 out of 36 divided by 1 out of 6. And what does that give you? Yeah.
30 over 36, which is 6.
Yeah, exactly. So 30. Yeah, exactly. And so steps here. 30 out of 36, which becomes 5 out of 6. Exactly. Perfect. Does that make sense, guys? Sorry, I just wrote over top of it, but that's the same answer. So we got 5 out of 6. Just erase it so you can actually see that. So, is everyone okay with that so far? So, 2 different ways I showed you, like I said, you can either use the formula or not use the formula. If I don't specify you have to use the formula, you can do whatever makes sense to you, right? But I'm not gonna lie, sometimes when people try to not use the formula, that's when they get really confused, because then they start drawing random stuff and then they're like, well, what am I drawing pictures of? Like they don't, like they lose track of what the outcomes are. It might actually, sometimes it actually will be easier just to use the formula, right? It just depends. Any questions so far? Let me know if you need more time with this. Is anyone confused with this? Just ask us. Okay. Hopefully this is making sense. Okay, and then we'll do another example in the next one. I won't use a formula. I'll just kind of switch it up a little bit, just to show you something different. And then the last thing we'll kind of talk about is when two events happen back to back and how we can use this to help us find the probability a little more. Okay, let's see another one. Without using the formula this time. Let's just see if it makes any sort of difference. So determine the probability that a roll of 2 dice will give you a pair, given that the sum of the faces is greater than 8. So I'll let you guys try this one, see if you can figure it out. You can, and again, you can use the formula, nothing wrong with it, but I did give you the picture just to help you speed it up a little bit. Yeah. Sorry? 10 over 36, yeah, and then you reduce it. So how are you getting that? Yeah. Yes, greater than 8 would be 10. That is correct. Perfect. You got it. So there's only the 10 right here that we're looking at, right? So we were told that the sum has to be greater than 10. So we're kind of limited to only these options. So 3 and 6, 4 and 5, 4 and 6, 5 and 4, 5 and 5, 5 and 6, 6 and 3, 6 and 4, 6 and 5, 6 and 6, right? So we're limited to only 10 outcomes. And of those 10 outcomes, exactly like Hope said, we're trying to figure out what's the probability that I produce a pair. So we're only focused on, so this is basically our sample space now. So the 10 outcomes that I circled in green is basically our sample space. And now my event space, what I'm interested in, is getting a pair in this group. Actually, I don't know why I picked red because the whole thing's in red. So how many pairs do I have in this little green group here in my new little sample? Yep.
Is an error double?
Yeah, double.
Oh, okay.
Yeah. Yeah, sorry, I should have said that. Double. Like 5, 1 and 1, 2 and 2, 3 and 3, 4 and 4, and so on. So how many pairs do I have in this group here? So I have 2, right? I have a 5 and 5, and I have the 6 and 6. So that means that so I can almost write it out in a different way. I basically can say that my sample space, that's my new sample space now. My sample space is 2. Actually, I'm just going to write 2, and then my, event space, I don't know why I wrote that, just my bad. It's all confused. My event space is 2, and then there's 2 of them there, and then my sample space here is going to be 10. So then going back to kind of the basics that we learned on the first day, if we want to find the probability, we take our event space, the number of outcomes in the event space, divided by the number of outcomes in the sample space. So 2 out of 10 gives us 1/5. Does that kind of make sense? So again, I explained all this step by step, but really you don't have to do this. I essentially listed them off all the outcomes, or exactly like Hope did. She just kind of looked at it and said, well, there's 10 of them all together. You can definitely just draw it all out. And we know that that means the sample space is 10, the event space is 2, has 2 of them there. So the probability is 2 out of 10, which is 1. And again, I showed every little step in between, but I did it more for like people reading the PowerPoint So that if for some reason they're not there, they can't find the video, at least they have the steps. Okay, does that make sense? Everyone understanding so far? Okay, are you sure? Okay. All right, so that's how we do that example there. So now we're going to do something a little different. So multiplication law for conditional probability. So this is the next little thing to write here. So you definitely don't have to write this formula because we already wrote it. But I'm going to show you how this connects with the next one. So what happens if we cross multiply and try to isolate for, actually, I already told you the answer. How do you isolate for the probability of A intersection B? Well, I already told the answer. You cross multiply, because by cross multiplying, you're moving the denominator to the other side, right? So when you cross multiply, or multiply by the probability of A on both sides, just doing a little bit of algebra here, this cancels out, and you actually end up with the probability of A and B is equal to the probability of A times the probability of B given, the probability of B given A. So we kind of just rearranged our formula. So you're probably looking at this and you're like, why would you even want to do that? Well, there's actually going to be a couple cases where you don't really want to know the conditional probability. Sometimes we don't want to know the conditional probability. We don't care, what's the probability of this given that the other event occurred. Sometimes we want to know the probability of two events happening side by side, right? One after another. So if two events happen one after another and they have an effect on each other, and again, we'll talk about that a little bit more tomorrow. So if two events happen one after another, but they affect each other, then you need to use this formula. And again, we'll talk about what this means. This is called dependent events. I'm not going to get to that yet. I'm going to do that tomorrow. So when events affect each other. So this is the formula you're going to use if you know that two events happen side by side, but they actually have an effect on each other. So up to this point, we haven't really done that with events, right? We normally had it so that they're completely separate and they have no effect on each other as far as we know, right? But in this case, we're going to be looking at events where the probability will change because of one event happening. And again, don't even worry about writing all this. This right here is just basically a little bit of a reiteration of what I already said. It's essentially just saying that this is the multiplication law that basically says that you can find the probability of two events happening at the same time. And just letting you know that, and I think Jessica, this is the question that you had asked earlier, like, does it make a difference the order you do it in? If you decide to write it in a different order, then this is the other version of the formula you use, right? But again, I'm hoping you're not just like memorizing formulas. But by the way, you are welcome, like, because we're a little bit more relaxed, especially right now, given the circumstances, we're kind of a bit more compressed. I will give you all the formulas. You have access to your textbook, that's fine. So it's not like you have to memorize these because you have them. But I hope that you're not just memorizing them, right? I hope you kind of understand them. So this is a different version of the formula. It's essentially just saying that if I have B already occurring, then I have to multiply by the probability of B, right? Because that's the event that occurred. Whereas this one is saying I'm going to multiply the probability of B given A, so the event that already occurred, I'm going to multiply it by probability of A because that already occurred. So just two different versions of the formula. So this right here is called the multiplication law for conditional probability. So we basically say that if you have two events that happen one after another and they affect each other, we need to use conditional probability to help us. Everyone okay so far? All right, so if I'm not mistaken, I think this is the last example that we're going to get to. Then we're done. And if I'm wrong and there's others, I'm so sorry. But I think this is the last one. Okay, here's another one. So let's say you have two cards. You're dealing out two cards, and you want to find the probability that you get two aces in a row. And the really important part here, and again, it's not really relevant right now, but it will be relevant more so tomorrow. Make sure you always read whether it's replacing or not replacing. That word makes a big difference, right? It's going to change your answer. So it actually does make a difference. In this case, it's saying that you're not replacing the card. So what I mean by that is if I am giving cards to, like if I'm playing a game, if I give it to Amelia, she takes a card, she doesn't put it back in the deck. So does that change the probability of choosing the next card? Yeah, it does, right? Because she took a card away, so now I actually don't have to do it, I have to do one. So that's what I mean by conditional probability. Automatically, because she took a card away, the probability shifted, right? So that's the whole idea of conditional probability. Honestly, if you understand that, that's probably the most important thing, right? That probabilities can change, right? It depends. In this case, it definitely does because we're not replacing it. If she was putting the card back, totally different story, right? We don't have to worry about it because the probability stays the same. So let's try this one together. So in this case, we have two different events happening, right? The first one is event A, that I get an ace in the first card. So event A is ace in the first card, and event B is ace in the second card. Right? So all I want to know now is basically how am I going to use those two ideas of event A, event B to help me find the probability of A and B. So what does the formula say? The formula says that find the probability of A and B. I just need to find the probability of of B given A multiplied by the probability of A, right? So let's start step by step. What's the probability of A? So what's the probability of choosing an ace? This is pretty easy. There's 4 aces out of 52 cards, so it is 1 out of 13. So now the next part is the part that you have to think about a bit more. What about the probability of getting an ace if you got an ace in the first round? How does that change your answer? Yeah. 3 out of 51. Does that make sense to everyone? It's 3 out of 51 because, like I said with the Amelia example, if she took one of the cards, now there's 51 cards, and because she happened to pick an ace, then there's also one less ace. So there's one less ace and one less card altogether. So it's going to be, this right here switches from 4 out of 52 to 3 out of 51, right? Because I lost one card, one ace, and I lost one card altogether, right? It's the same card, but I lost it from both spots, I guess you could say, from both spaces. So my next step here is I realize that my probability of B given A, which is essentially the probability to get a second ace, given that I got a first ace, is going to be 3 out of 51. And again, that's exactly what we just talked about. Again, you don't have to write this because we literally just talked about this in class, that because Amelia took one of the cards, there's one less card, one less ace, right? So because of that, it becomes 3 out of 51. And again, always try to reduce it. It makes your math a little bit easier. That becomes 1 out of 17. And then what does the formula say? Formula says that if you want to find the probability of A and B intersecting with each other, the two events overlapping, I need to take the probability of B given A multiplied by the probability of A. So all I got to do here is just multiply this times that. Does that make sense? So all I'm going to do here is just multiply the probability of B given A, which is 1 out of 17, times the probability of A, which is 1 out of 13, and just multiply across. Multiplying is really easy with fractions. You don't need a common denominator. We'll still make that mistake a lot. No common denominator, just multiply. and you're done. So it's 1 out of 21. Does that make sense? So just a question, what would it be, and we are going to talk about this later on. What if I did put the card back? So what would the probability be? And again, I know the number is huge, but just even tell me what you do. Sorry? So it would be, so if I put, that's a good guess, but so it's going to be out of 52, but because I put the card back and it's an ace, it's still going to be 4 out of 52. So it's going to be 4 out of 52 times 4 out of 52. So nothing really changes. I'm just multiplying the same probability twice. So it only changes in this case because I didn't replace it. Okay, so because I didn't replace it, then I have to use this conditional probability that I know. Does that make sense? All right, and I think that's, that's kind of everything. Is it pretty good? Hopefully you found that one a little bit easier. I don't know, maybe I feel like some of the examples were like, because of the format, it seems confusing. It's actually not too bad, I think, if you just think about it. So, guys, I'll let you guys take a break. It's definitely been a long day. Feel free to stretch. Anyone needs to go to the washroom, you can also do that as well. I forgot to mention, if you want a snack, I'm okay with that too. You can have a small snack as long as you clean up after yourself. So there's a homework there right out after.